I'll talk. I'll talk about spray routing DSL today. How many of you guys were at the Akka-Http session today? Good. This presentation will use code only, not necessarily live coding, but all of it is code. So you'll have to read a lot of code. So if you can't read it, please come closer. And all of the code that I'll be using today is of course also on GitHub. You might still have to push some latest updates, but most of it is on GitHub. And the link is already also at the end, so you can check out fully working examples. So the plan for today is to give you an extremely short introduction to Spray, because yesterday's session already gave you a pretty good feeling for what Akka-Http and its predecessor Spray do, what it's good for, and why. And I'll show you a very simple example, what it looks like, how to run it, how to test it. I'll try to explain a bit about the underlying mechanisms, how it works, and then based on that, look at some real-world examples. So something beyond the basic example, what can you do, how to solve difficult problems. And there's a Q&A at the end, but if what I'm saying doesn't make sense to you at all, please feel free to raise your hand or start shouting. So, very brief introduction to Spray. As Matthias already said yesterday, Spray is an HTTP toolkit, which means it's not a framework. It doesn't prescribe the way that you should write your applications. It's just a library, but it allows you to write HTTP servers and HTTP clients using an immutable HTTP model, which is very, very complete, and also very much it matches the HTTP spec extremely well. So everything that's in HTTP is exactly correct in Spray, which does mean that if you have really old clients or clients that don't really follow the HTTP protocol all that well, and sometimes Spray might be very strict. And there's usually a way around that, but it's something that you have to keep in mind. Of course, because it's built on top of Akka, it is 100% non-blocking and asynchronous, which means that it's also fast. And it makes it hard to shoot yourself in the foot. Of course, it is possible. Spray routing, what we're going to talk about today, is a module in Spray. In the Akka-Http version, all those Spray modules have been flattened a bit, and there's only the core model and the top-level HTTP module with the routing inside. But in Spray, it's still Spray routing, which is a type-safe DSL for handling requests, producing responses in a functional, composable way. And we're going to see what that means and how it's different from frameworks like Play, ScalaIO, and all the others, where there's only one level, which is the URI. You match it, and then you do all the rest in some other code. And last but not least, Spray CAN is the lower level, which allows, it's a full HTTP server based on Akka, and when you run Spray applications, you're almost always going to use Spray CAN to run it. At the moment, there's still a servlet version, which allows you to run on servlet engines, but the Akka-Http version no longer will support that. So Spray CAN is super fast, and I can recommend running everything on Spray CAN. And as Matthias already said, Akka-Http is pretty much Spray 2.0. It's still being developed, but by the end of the year, it should be pretty stable when it comes to the why spray? I think I've already mentioned a couple of things, but for me it's the type safety, the asynchronicity, and just the DSL is very elegant. In my experience, some people think it's a bit complicated or complex. You do have to, it does a lot more than play, for instance. But I really like it. And the best part, of course, is built on top of Akka. So if you have an Akka application, and this is the closest way to build HTTP using the same thread pools, the same everything. Unlike play, there's no netting involved anymore. So just Akka. I've been using Spray since about 2011, version 0.8, 0.9, somewhere on the edge there. I have a couple of contributions, a couple of directives and bug fixes and stuff like that, but I'm not one of the core team. That's Matthias and Johannes. And I've been using it in production on production apps for the last 3 or 4 years without any problems whatsoever. It's definitely production ready. So let's look at some basic examples. I hope this is readable to most of you. What we have here is, of course, we need some imports, spray routing, and a couple of utility stuff. Well, that's also, by the way, better in Akka-Http, where you need less imports. Everything is squashed together a bit better. Because we're built on top of Akka, we need an actor. So Spray runs as an actor inside the Akka actor system. We need some routes, some way to handle HTTP requests, and it's very common to run that or to build that in a separate tray to make testing a lot easier. We'll see that in the next slide. So you don't have to test your spray routes using the actor test kit. You can test them separately. It's sometimes very handy. Then the receive method of the actor is implemented using a method called run routes, and we'll have a look at it later what that actually does in how it works section. But all it needs is some kind of definition of a route handler, and that's in the code below. The API routes is some kind of function that takes a request and somehow produces a response. Again, we'll see how that works later. And what we see here is we match on a request on URIs. So if the path of the URI starts with API, and then if it has API/things, and then nothing else, and a GET request comes in, we produce some content. And if on the same URI we get a post, then we unmarshal the entity in the post, do something with it. So the way Spray handles routes is to build a tree of route handlers, and the request comes through. If it matches one specific route, then you end up in a completion, and otherwise it just falls straight through, and we'll see what happens then afterwards. Of course, testing, very important. So I thought I'd start with some to show you how you test things. Spray has a test kit just like Akka, and part of that test kit is this trade Scala test route test. There's also a Specs 2 version, and the only thing and what it gives you is a way to execute your execute requests against your route handler, and then check the behavior, check the responses that it produces. You need an actor refactory, otherwise known as an actor system, so that And then you can start firing requests. So here, there's a GET request. We use a little DSL sort of squiggly arrow there to pass it through our API routes. And then we have a check block where we say it should produce an OK status. It should produce a content type of application JSON. And if we unmarshal the response to a list of things, which is what we expect, then there should be two things. And same for doing a post, it should produce a created. All the status codes are in the status codes object, so you can easily mash them. And the same goes for headers and all the other parts of your HTTP spec. They're all predefined and you can easily mash them. And content types sometimes takes people a bit of time to get used to the content types with the quotes around them, but it does make it very clear what kind of content type you match. I kind of grew to like it as well. So when we execute that test, just as you expect, it produces requests, it checks the responses, everything works fine. So now we have an actor. It does HTTP matching. How to run it? Just to make a simple main class, we need an actor system. Of course, because we're running on Akka, we instantiate our actor, and then we use the I/O extension, the Akka-IO extension, with the HTTP actor, pass it the system, and then all the last thing we have to do is bind to a port on the interface. I use sending it the bind method message. That's it. Your actor gets started. It listens on the port. You send it requests, and it will pass through the API actor, and your routes will get the route handler gets executed. So if you run that, there's a very cool SVT plugin called Revolver, which makes it very nice to do iterative developments. Here I just executed once, but you can also run it in a continuous way, so that every time you change your code, it just restarts a forked JVM with your code running. And then, as you can see, you can send it requests. It will produce some JSON, and if you want, you can stop the machine. So that's the basics of running a spray-based system. So how does that work? What is actually happening there? So the first thing we need to talk about is routes. And at the core, spray is just a function that takes an HTTP request and somehow produces an HTTP response. The actual type route is implemented slightly differently. In Spray, in Akka-Http, it's exactly like this. But in Spray, you get a request context, and it produces nothing because the response gets produced underwater and gets sent to an actor. You don't really need to know much about this, but a route is a function that takes a request context and produces unit. So if you look at the code we just looked at before, then that is a route. The whole tree is a route. And the route is composed of directives and routes. The complete call over there, that's a route. And you combine and compose them using directives. So here's a simple route. One of the simplest you can possibly have. Any request that comes in, whatever it is, gets completed with a plain text message that says woot. what it actually, you can also write it like this. It's actually a function that takes a request and produces wood. If you want to make it even more literal, then this is really what happens. It takes a request context and you call complete on the request context with some data, and that gets sent out as an HTTP response. If you look at a slightly more complex route, this only reacts to GET requests, so put requests, delete requests, etc. Will get ignored, or at least nothing will happen in this code. Then you can rewrite it as an inner function that does the complete, and then the GET directive can take that inner function as an argument, which produces a new function, and whenever a request comes in, that function gets executed with the request. So it's very functional in the way it works, and that allows you to compose very powerful structures, as we'll see later. But the way this currently works in Spray does make it sometimes produces weird behavior. Luckily, this is solved in Akka-Http, but if you write code like this, where inside a directive body you have some side effect, what actually happens is this. It will produce a val, and the print line will get executed while building the routing structure, not while executing the routing structure, but while building the routing structure. And this is probably the most asked question on the Spray event list. Not only print lines, of course, but logs, code with side effects, anything that is not in the leaf node of the tree will get executed when the tree gets constructed, when the class gets instantiated instead of when the code gets executed. This is there's a way around this, which I don't have a slide for, but in Akka-Http this is solved. This is very unintuitive, and it leads to a lot of questions. But you can work around it by making the route dynamic, so wrapping it in a dynamic. There's a directive called dynamic. You put that around this, it will make sure that everything only gets executed when the function gets executed. And there's some basic ways of composing directives, or composing routes. So this structure, if a request comes in, it first checks, is it a GET request? If so, then it completes. Otherwise, it's a sort of a depth first search. So it goes in, doesn't work, goes out again, tries delete, still doesn't work. Then you can also use booleans to see if it's this or that. So that's some low-level ways of composing directives and routes to build a tree. And of course, this is the first forward reference to the Spray documentation, which is very good. And I don't have the time here to go into all the details, but the documentation definitely does. It's very extensive and gives you a lot better explanations of what's going on, what are all the ways of composing routes. So please have a look at that. So directives, we've mentioned directives already, and what you see here, path, prefix, path, end, get, post, entity, they're all directives. And directives are hard to explain. So what I've done here is just copy-paste a bit of documentation. With the directive, it allows you to either transform a request, so add stuff to it, so add a header to it before you go deeper down the tree. change other parts of the request. You can filter requests, just like we've seen with GET. And so if it's not a GET request, GET will filter the request. It won't get, it won't go deeper. You can extract values from the request. Anything that's in the request, headers, cookies, URI, whatever you can think of, you can extract it and make it available for the inner part of the tree structure. And of course you can complete requests. And there's a very good documentation about this. It goes a lot better, deeper than what I can do in the limited time I have here. And Spray has a lot of built-in directives. This is the full list of high-level traits that contain directives. So just about anything you can do with an HTTP request, there is a directive for it. So matching parameters, matching form fields, matching headers, finding cookies, adding caching, adding support for serving files, all of that stuff is taken care of. All you have to do is combine them together into a routing. We'll see quite a few of these combine in the examples. So, what happens when you call run route? It's an actor, so run route has to implement the Akka-Http type. It has to do some matching of messages. So you don't have to read this, but underwater it takes your route, which is just a function. It adds default exception handling, default rejection handling. We'll talk about rejections later. And some other stuff. And then does actual Akka code, matches HTTP requests, creates a request context for you, and then runs your function or routing function with the request context. So underwater, it's just an actor that matches messages, produces other messages. So if you look at the code, you see that I call complete with a list of things. How does that get transformed into JSON? If you look at the import statement, you'll see one reference to JSON, and that's all. It's the import for Spray JSON support. And that's it. The rest magically happens, and my list of things gets transformed into a JSON structure. So how does that work? The complete method, also pretty complex code, but it takes your T, and somehow there has to be a marshaller for your type. That marshaller is a type class, so somewhere in the implicit scope there needs to be a marshaller for your T. And what the marshaller eventually produces is an HTTP entity with a content type and some value. That value is usually a byte stream or a byte array. So all of this code is just a wrapper, but when you have T and there's no marshaller in implicit scope for what you're trying to complete a route with, then we'll get a nice exception or a compiler message that says we cannot produce anything with the content type and byte stream from this. And what you see here is a brief bit of some of the standard marshalling, the basic marshallers that are in Spray. They're pretty low level, so anything that is byte arrays, byte strings, strings, and HTTP responses and bridges like Rejection support that take care of lists and your case clauses and all that kind of stuff. And if you look at Rejection support, Rejection is a type class-based JSON library, so usually you need one line of code to produce a JSON reader or JSON writer for your case class. And this will create the bridge between the marshallers in Spray routing and the readers and writers in Spray JSON. So it takes, it only matches on application with JSON, so if the content type is different and this doesn't do anything, it doesn't match, and you'll need some other marshaller or unmarshaller. And it just does the JSON parsing for you and produces and maps it to your case class and the other way around. Marshalling also is explained in great detail in the documentation. And in Akka-Http, the marshalling infrastructure is greatly simplified. Because at the moment, the reason why I'm having trouble explaining it is because it is quite a complex subject matter with a couple of layers in between, and a lot of implicits, and a lot of that is gone in Akka-Http. It's a lot simpler. Rejections. So what happens if I send an HTTP request into this routing structure and it doesn't start with /API? And it falls through the entire tree, and nothing matches. It comes out at the end, and somehow the Spray needs to produce a response to this. It has to produce some kind of response, because otherwise the HTTP connection doesn't produce a response, and you hang and eventually time out. So somehow it needs to produce a response, and it does that using a rejection handler that interprets rejections and turns them into HTTP responses. And rejections are just case clauses that have to be produced by directives. So in our example here, if you send a delete into this tree structure on API/things, then it sees, okay, I support gets and posts, but not deletes. So that you get a negative rejection. And if that's the last rejection you have, then you get a nice response that says this API exists, but we only support gets and posts. So rejections are a way of giving the person or computer that sends the request to you as much information as possible about what's wrong. Why is there no match for your request? And if you look at this is just a snippet of the default rejection handler. As you can see, it produces plain text, and it always tries to give as much information as possible about what went wrong. So the method rejection is there, HTTP method not allowed, supported methods, and then the list of methods that are allowed. So that's really handy, because you don't have to worry about all the negative bits unless you want to produce different default responses. If you want to produce JSON error messages, for instance, then you have to do something. But if this is good enough for you, then all you need to do is support the Highlevel basically, and this takes care of everything that doesn't match. Of course, you can test that. I had a couple of tests for things that don't match. So if I do a put, we say, sorry, we don't support puts on this URI. Handled is false, so it doesn't actually handle nothing in the tree structure matched, so it wasn't handled, and it produced a rejection, namely a meta rejection. If nothing matches and there is no rejection, that means that basically 404. There's no URI found that matches, and the default rejection handler will produce a 404 and not found response. So if I send a GET request to the API unsupported, I'll get an unhandled route request and rejections is empty. Later, a little later, we'll show how you can customize the rejection handler to do stuff that isn't supported by the default rejection handler. But this is usually good enough for most people. And of course, I'll link to documentation because this is also important. So that's some of the very basic underlying structure that Spray gives you. Most of that I learned, I had to learn later when I wanted to do more complex stuff. But the basics already work good enough for most applications. So you don't need to know all of this to get started with Spray. And the next section is going to show taking this basic stuff and then show you some more handy examples from the real world. So let's start with composing routes. Most applications I've written with Spray are not as short as the default examples. There's not one URI with a couple of methods and that's it. It's actually most browsing structures are pretty damn big. So what we do is split them up into traits. So we have API routes, we have asset routes, and then we compose them together like this. And in the latest application that I've written, we have about, I think, 10 top-level routes, and then those top-level ones are again contain. They match usually in API / something, and underneath you split it up even more. And because the route structure is very composable, it allows you to do this. It allows you to spread your code, split up your files to make it manageable. Because otherwise you have one giant tree somewhere, not very reasonable. So that's it. That's how you compose routes. There's a lot more. That's it. Sorry. So something that I usually turn on immediately when I write a Spray application is support for gzip and default, which usually speeds things up nicely, and it's sometimes hard to find how to do this. That's why I added this example to the presentation. So what we're saying here, as the highest level directive that we're using here, is decompress requests if they are compressed, and if the requesting party supports compression by sending a correct header, accept header, then compress the response. This is completely optional, so if the request is not compressed, we don't decompress it, and if the request doesn't support gzip or deflate in any way, then it's not compressed. But this one line takes care of gzip compression. It prefers gzip over deflate, but if you only support, if your accept header says deflate, then you do deflate too. And that's it. That's how you support gzip in your route structure. Oh, we had a look at at the rejection handlers before. So what the last couple of applications that I wrote were REST APIs that were used by usually an AngularJS application, and we serve the AngularJS application, static files basically, also from the same application. Which means that for some URIs, starting with API, you have certain behavior. That's the REST API, but for other URIs, other requests, you want different behavior. You want a different, if a request comes in and it's a 404, then you want to produce a 404 page instead of a JSON response. And that's very easy to do in Spray by using the handle rejections directive at a lower level. What we're saying here is we have an API rejection handler, which is just in this case a default, which I'll show you how to do a more non-default one next slide. But we have some kind of rejection handler, and we handle all rejections underneath API. So if it goes into API, if your request starts with API, and it somehow doesn't match 404 or anything else underneath is wrong, then it will use the default rejection handler to produce a response. Whereas if, for instance, you have a route that serves static HTML pages, you can use this one. Straight from my current project, we have two rejection handlers. It's a public-facing website, so they don't really want to see any details. So if it's a 404, we show the 404 page, and if it's some kind of other error, we show the internal server error page with some details, try again button, etc., etc. So this is a very, very limited but good enough rejection handler for if your request is for a static page. It's definitely not good enough for a REST API, but for static pages, this is all you want usually. Underneath there is a rejection handler that I wrote when implementing an OAuth 2 server. The OAuth 2 spec is very, very detailed in the type of responses that you have to produce for error situations. And Spray makes it very easy to do that. All you need is to produce a partial function that takes some kind of rejection. And in this case, some of those rejections are custom rejections, rejections that our code produces. Other ones are default Spray rejections, like missing form fields, malformed form field, malformed REST content. These are all standard rejections that Spray produces if your request is wrong in some way. There's in OAuth 2, there's only a couple of different rejections or responses that you can produce in case of errors, and those we produce. And you can see if anything else is wrong, so it's not covered by the OAuth 2 spec, but it still gets rejected, then we just combine the partial function with a rejection handler with the default rejection handler, and it falls through into the default rejection handler. That's a nice way of composing rejection handlers to do custom work. Another thing that we do a lot is, in this example, is add cache headers. For API, we usually turn caching off. And the respond with headers directive is a very easy way to do things, to do that. It has support for the cache control header, which is a built-in structure. No store is also a built-in structure. Unfortunately, that one is not supported. If you want to produce a header or read a header that is not supported by Spray, you can always use raw header, which is just a key value there. So we produce two HTTP headers here, one with cache control no store, one with fragment no cache, which the spec says that you have to produce. And any request that makes it, that starts with an API will always produce those two headers. And whatever happens underneath happens. So even rejections, not rejections, but whatever gets produced by Things API routes and Use API routes will have these cache control headers. And for static files, we usually set them to cache keys for a day or a couple of days or whatever. So Spray has a lot of directives, but sometimes you want to write your own. Sometimes it is because your route handling code becomes very repetitive, so you do the same trick a couple of times. You want to basically apply an extract method, and you can do that by creating a custom directive. Any couple of directives that you can compose together using the standard compose operators can be stored in a val and then reused to build a routing structure. But sometimes you want to go a little bit further. So the example that I have here is I want to enforce HTTPS. I do not want to support any request coming in over HTTP. And if there's a request coming in over HTTP, I want to redirect to the HTTPS version and set the strict HTTP strict, set the correct header that says you can only access this website, this REST API through HTTPS. So you can use it like any other directive. It looks exactly the same, but it saves a lot of code sometimes to say things in one line instead of the whole structure that you would need. I just add an HTTP directive straight. That's where my directives are, and this is what it looks like. Directives, I kept it simple. Directive 0 is the simplest structure to use. It basically doesn't produce an extraction. It doesn't whatever gets wrapped inside doesn't get any extra parameters. So sometimes in development I want to run allow HTTP because otherwise I would have to run an SSL server locally. So I made a directive called enforce HTTPS if. Takes a function and produces a boolean. We usually get that from settings. And if the boolean is true, then we enforce HTTPS and otherwise not. And enforce HTTPS always sets the strict transport security header, and then it extracts enough data to be able to determine whether it's an HTTP request. That's the function in the bottom. So if your scheme, if your UI starts with HTTPS, that's good. Or if you have an exported proto header that starts with HTTPS, that's good. Otherwise, it's not HTTPS and therefore wrong. So you can see that you can match headers at the lower level by just matching if it starts with string. So extract is a directive that is one of the core directives that extracts a piece of data from an HTTP request. In this case, it produces a boolean, but it's a directive. I'll have to start talking for a lot faster. So it's a directive, and if I want to do something with a directive, I can't just embed code, nest code inside. I'll have to call flatmap to produce another directive, because it's all composed functions. Extract produces a directive. If I want to produce a directive too, I can use flat map. And in this case, when I say, is it HTTPS? Yes, then I just pass, which is a built-in function that just allows anything to pass through. Otherwise, I redirect to the HTTP UI. That also uses flat map and just takes the existing UI, changes the scheme to HTTPS, and then produces a redirect 301 response. So it's a pretty basic example, but it shows that it's very easy to write your own directives. I've written directives for doing authorization checks. Is the cookie available with this value in it? And it allows you to, just like you extract a method, to have some repetitive code without duplicating everything. It allows you to do exactly that for your routing scheme. And my last example, so I am super on time, is working with futures. Because all the examples, all the basic examples usually produce static content, hard-coded list of things, for instance, that we just had. But what if you have to talk to a database or some other remote system? Usually have an API that looks something like this, and it produces futures. You don't want to block. If you block inside a route handler, then you block the actor that handles requests, which means that your throughput will go way down. So you should never block inside the route handler, which means if you want to do, if you want to call out to other actors or other asynchronous code, then you'll have to be able to work with futures. So this is our API. It's a simple store. It stores dudes, and it gives you the basic code operations for things and dudes. So we just mix it into our API. We'll get the implementation somewhere at the top level, but this is just the trait that defines the interface. And because we're working with futures, this is, I constantly forget, still constantly forget to do this, but when you work with futures, you need an execution context. If you don't have an execution context, then the compiler will produce errors. In some cases, especially with Spray, those errors can be very confusing. But if you're working with futures, you need an execution context. So what we have here is a simple trait that provides one as an implicit value. And then the complete directive has native support for treating the futures. It doesn't block it. It will just complete when the future completes. So if all you want to do is whatever comes back, whenever it comes back, produce a response from it, this is what you need to do. Make standard support. But sometimes what comes back, you want to map over the future to produce something else, or you want to only do something if it's successful. So there are some more directives. The on-success directive is the one that we use the most, because what we usually do is the store place produces some domain objects, but all the translation from the domain object to something that goes into an HTTP response belongs in the HTTP layer, not in the store. So this is where we usually do translation. In this case, I wrap the ID of the newly created dude in a JSON object, and I have great JSON support in my imports, so I can produce a raw JSON just as easily as case classes that have to JSON. Can you nest on success? Yeah. So you can, if you have multiple sequential operations that are asynchronous, then you can do multiple future calls in a row, nested. That's not a problem at all. And you can also do anything you would normally do with futures like map them, flat map them with other futures, etc. And eventually the future will complete, produce something, and then spread it with the rest. And here, same thing basically. I get something back and I want to produce different responses based on what comes back, different status codes. So I do simply pattern match. So that is the end of my presentation. I hope that I gave you a little bit more insight into how to use the spray routing DSL, some simple examples of more advanced things that you can do with it. As always, the spray documentation is very good, so there's a link there. And the code, way more code than I showed here, a complete working application with all the stuff that I just showed you is online at your own. And thank you. Can you put rejection handling? I think that's what you mean. Inside the tree, and the answer is yes. Let's see. Like we show here, the handle rejections call with the rejection handler is just a part of the routing tree. So anything that goes in produces rejection gets handled by this rejection. So in the case where it's described where we have a REST API website. We have two nested rejection handlers, one for the API and one for the website, instead of the default one that only gets applied at the very top. So we have custom behavior for subtrees of domains.
And you can write in there like another directive?
Yeah, it's just another directive. Indeed.
That's right, so if you have one higher and lower level,
the first one, the lowest one that surrounds it, can do that, and they don't have to overlap. So if you only want to catch a very specific rejection at the low level, then you can wrap it with handle rejections and have a rejection handler that only does one thing. And then at the higher level, you have to catch all the defaults that takes care of the rest. So you can match them wherever you want.
Is it compatible with Swagger?
It's compatible with what?
Swagger. Is it compatible with Swagger?
Swagger. Also, a question that gets asked a lot on the mailing list, and the answer is unfortunately not. Because unlike most other APIs, the entire structure of the URI matching is one function. And that function just gets executed, but there's no code, there's no annotations that you can read at compile time. There's just a function, and that function cannot produce the necessary Swagger. There's no way to generate the Swagger description from the function. Unfortunately, it's a pretty hard problem. Matthias?
Yeah, it's true, you can automatically generate it, but you could still manually generate it if you want to, right? So it's possible to just serve the JSON that Swagger needs in order to show your documentation. That's possible, no problem. But what most people are looking for is that you don't write the documentation, right? It automatically gets figured out from your definition, and that's currently hard. and it will be hard in the initial version of Akka-Http, but there is a subsequent version of Akka-Http already planned where this will be fixed, because then the routing structure will be inspectable at runtime, and then it will become easy. But we won't make this really breaking change right now, because we want to make it easy for people to migrate their stuff, and lots of the applications that Akka has shown and so on, they will be quite easy to be migrated to Akka-Http. And then once everyone is there, we can gradually introduce a completely new and improved, even more improved routing DSL, which then will make things like automatic Swagger documentation easier.
Okay. So there you have it.